is Rachel, and I'm a science educator with the Exploratorium. Today, I'd like to focus on the science and engineering practice of modeling. In this case, a teacher and I made a small change to an existing lesson, a subtle shift, to engage students in the process of making models in order to help them form explanations and explain their ideas to each other. This is an example of adding modeling on the fly. It was not in the curriculum, but we added it based on our formative assessment during the lesson. After doing an activity and having some discussion, students asked questions that showed they did not understand what the lesson was meant to show. Adding modeling here was a way to help them do more thinking to get more clarity about what was happening. Kids had explored magnets, seen that they attract and repel, and seen them interact with other objects. They saw that there's a push or a pull to the magnet. This lesson was supposed to help them see that there is a strength to that push or pull that gets weaker with distance. How this lesson worked was there was an equal arm balance with two cups in it, and a magnet was placed in a cup on one side, and underneath that cup there was a magnet on the post, and those magnets were attracting each other. The students put washers in the cup on the other side of the balance and counted how many it took to break the force or separate the two magnets. In each trial, there was a plastic spacer put in between the magnet on a post and the magnet in the bottom of the cup to increase the distance between the two magnets. And the students then recorded the number of washers that were required to break the force when there was one spacer between the cups, two spacers, three spacers, and on and on. Each group plots their data on a class chart with sticky dots so that the teacher can discuss the data with the class as a whole. In this original lesson, there was a short, maybe 5-minute discussion where the students were supposed to interpret this graph and see that the farther apart the magnets are, the weaker the force between them. The teacher, however, found that the students were confused by the data, and only 1 or 2 kids seemed to get that there was a relationship. Oh, excuse me. We added a science talk to the end of the lesson to help students make sense of the graph, and realized when the students we realized during this time, as the students were talking, that because the graph does not show a linear relationship, the students were confused. At this point, we made a shift to the lesson to include the cross-cutting concept of cause and effect relationships, which I highlighted in another video. While we were discussing the data, a student raised the following question, which we did not expect during the science talk. It was surprising because in prior lessons, students were already supposed to have learned that magnets work through things. So we turned the question over to the class. As students were explaining their ideas to try to answer the question, it was clear that the other kids did not understand the ideas being presented. So we asked the students to draw what they were saying to help others see their thinking. This was a spontaneous subtle shift because of what was happening during the science talk. The kids didn't understand what each other was saying, so we asked them to draw their ideas on the board. The kids in this science talk were seated in a circle, and they were all facing each other, but they were pretty close to the board, and most of them could see, all of them could see the board. Some of them had to turn around to be able to see the board. But we asked the kids to go to the board and write their ideas, and it was challenging for this first student to draw her ideas on the board. And even after she drew her ideas, we realized that the diagram was still too confusing for most kids to be able to read. So we asked her to label the parts of the diagram to help her readers understand her thinking. She also then explained her diagram, and what she was trying to show was that she did think magnetic force was working through things like the spacers or the banana chips. We realized in the course of this drawing experience that there were a few tips we could share to help the students make their thinking visible. For one thing, we asked the students to use different colors to represent the different parts of the system. So in this drawing, the magnets are one color, the spacers are a different color, and then ideas about the magnetic field are represented in different colors. We also asked each student to explain the parts of the diagram to the class. This student said that he thought that there was one magnetic field that went around both magnets, even when there were spacers in between. He first drew the red indented circles to represent the magnetic field. As he was speaking, he said, "Well, I think it is one big magnetic field." And then he drew the purple circle around the whole system. One thing that worked in our favor here is that it takes some time for students to draw their models. And how that worked for us was we had the kids do a pair share about the prior model. What do you think the author's purpose was? What do you think the student was trying to communicate to you? And that gave the students additional time to process the ideas of their peers and try to understand them. And it gave the kid up on the board time to think about his or her drawing, which takes some time, especially when kids are new to this. This particular student was expressing his idea that there was an edge to the field, but that as long as the magnets were close enough, there was a magnetic field between them. So here, the orange lines are the spacers, but those red ticks by the line are representing a magnetic attraction that works through the banana chips. In addition, this student drew a blue circle to show that there was one magnetic field, one big magnetic field. And it really seemed like he was attempting to reconcile these two different ways of looking at the magnets. Is there one big field or are there two different fields? This student is showing the idea that each magnet has a field, and if there are enough spacers in between the magnets, their fields would not touch or interact. After these models were shared, we used a consensus model to make a conclusion statement. First, we asked the students to pair share about the original question and the ideas that they had seen. So as a pair, they talked about, does the force of magnets work through banana chips? After several pairs shared that they thought that they did and used either the models for evidence or evidence from the lesson to support their ideas, I wrote the first sentence and asked everyone to put a thumbs up or a thumbs down if they agreed that this represented our thinking. Then we had to tie this back to the original lesson and say what this meant in terms of the experiment where we broke the force between magnets as they became farther apart. The nice thing about this consensus model was that everyone got to participate in the conclusion, even though not everyone was articulating it one at a time out to the whole group. In terms of developing language, the process of modeling is very helpful. It provides a visual representation that helps kids access language and science concepts. And by doing a turn and talk after each model, more kids had an opportunity to talk and listen and be successful in mulling over the ideas presented. This worked really well because they had previously been taught how to turn to a partner and had a lot of practice and feedback with that protocol. What I'm learning with NGSS implementation is that the students benefit enormously from making those visual representations, not just the teacher making the representations. Having students not only produce models, but use them as a basis for class discussion is also very productive. It was easy to add in the practice of modeling in this lesson. Many of us are working with curriculum that was written before NGSS was adopted. But what I'm learning is that we really can make subtle shifts towards NGSS with what we have that will not only help us understand the elements of NGSS better, but it will help the students better understand the material we're trying to teach.